Okay, so today we are here for the last tutorial session of this course. Let me share my screen first. If at any moment you guys are unable to hear me, then you can speak or you can text in the chat, okay? Is my presentation visible? My screen is visible or not?
Yes, ma'am.
Okay, okay, then let me start. So today is the last session of last tutorial session of this course, that is technologies for clean and renewable energy production. So firstly, let me give you a brief summary kind of thing what we have studied till now. So in this course, it basically is about the uh, various routes for the production of energy from different kind of fossil fuels, and then we studied about various renewable energy sources. So firstly, we studied the energy production from solid fuels, solid non-renewable source that is widely used in India, that is coal. Then we studied the energy production from liquid fuels, that is petroleum, then from the gaseous fuels, such as, that is syngas, natural gas, etc. And further, we move towards the renewable energy production, renewable energy sources, and various routes for energy production from that. And we studied solar energy in that, wind energy, then hydro energy, and geothermal energy, and tidal energy. And today is the last one, which is the biomass energy, which is also widely used source of energy in India. As we know that we are a country where agriculture and is one of the most common occupations. So we have a lots of biomass, bio waste and biomass here. So it is also one of the widely used source of energy. So we'll be here studying about different energies and different kind of biomass and waste, what kind of biomass is available and how we can use these biomass convert to harness the energy present in them for the usage in various applications, such as in the form of fuels in houses for uh, such as for biogas for etc. in our houses. So the content for today is biomass and waste, biomass and waste as a source of energy, and biomass and waste to energy conversion route, various energy conversion routes we will be studying, mainly the three kind of energy routes. That is, the first one is biological route, then chemical route, and then physical route. These three routes we will be studying. So here we will be talking about the biological route, which is mainly the anaerobic digestion. Then chemical route, we will be talking about transesterification, and then uh, why upgradation, why we need to upgrade this biofuel. We will be talking about that also. So why do we need to process the biofuel? Why can we cannot use it directly? Different kind of bio oils are present, which are derived from oil seeds. So why we cannot use this bio oil in its original state? Why we need to upgrade it? That also we will discuss. Then comparison of different kind of biofuels we will be talking. Then densification is, this is the physical method, physical treatment. What physical treatment will be is needed to to be given to the biomass for its better properties, for better handling, etc., better handling, transportation, etc., that we will be studying, which includes densification. And then lastly, this is not the part of biomass energy. This part is basically we will be talking about that apart from all these forms, about apart from all these states, harnessing energy from different sources. such as sun, wind, tidal energy, there are other ways also how we can how I mean basically man made rules and regulations which are needed to be followed, which we need to follow so that we can conserve energy. We can use lesser energy to produce same amount of work. So this is basically a general thing we'll be talking about little about energy conservation to wrap up our this subject. So coming on to what is biomass and waste as a source, what is biomass and bio waste and how it can be used as a source of energy. So basically, biomass is the bio waste and biomass is basically the uh, uh, remains which we get from the agriculture and then from animal excreta, human excreta, all those comes under bio waste. So basically, it includes grasses, then corn stovers, bagasse from sugarcane industries, then wood chips, etc. I mean, any kind of agricultural waste comes under. It consists of different components. Basically, the most abundant component is cellulose and hemicellulose, which is in 38 to 50% and 23 to 32%. And some other minerals and some other components may also be present. And moreover, it consists of this lignin part, which is basically not required. If we want to extract energy, then we sometimes need to eliminate this lignin. We sometimes need to pre-treat to remove this lignin from our bio waste. Bioma. This is the these are some different kinds of sorry, some different types of municipal waste which are present, which is shown here, along with their moisture content present in them and the heating value. Their different heating values. So some of the bio waste it includes paper, cardboard bags, wood crates, boxes and scrapes, bush and branches, leaves, grass, garbage, then green stuff, greens, rags, cottons, moreover the waste from our kitchens, then human, human excreta such as cow dung, etc. That also comes under biomass. So here we can see it also consists considerable amount of moisture, and as we know that if the moisture content is more, then the heating value will be low. So we can see here that this one, garbage consists of the largest amount of moisture, so it has the least heating value. Whereas here, paper, cardboard bags, etc., it consists of very small moisture content, therefore the heating value is also very high. Now coming on to some of the routes for energy production from waste. Basically, biomass can be treated in various forms. Various techniques can be used. So, as we know that biomass is basically plant remains. So, as we have studied earlier, that coal is also basically plant remains. So, we can say here, but here biomass it is not stored for many years. We know that plant waste, when stored for millions of years, it converts into coal. It forms coal. But here it is not stored for a long time. So we can by this we can say that we can use various methods to harness energy from biomass, which we used in the energy harnessing from coal. But the reaction conditions are to be varied because here we know that moisture content is very high compared to coal. So some of the techniques are so mainly coal. If we use similar techniques as coal, then they come under thermochemical conversion. But we have studied all this in detail during coal, so these are not discussed here again, which is the combustion, gasification, pyrolysis, liquefaction. All this we studied while we studied about coal. So from gasification, pyrolysis, liquefaction, we can get FT oil, bio oil, heavy oils. The important techniques which we will be discussing here are below, which is the biological conversion. If the moisture content is very high, then mostly we use the biological conversion method, in which anaerobic digestion is the main, which we will be talking about in our lecture, in our first lecture. Then fermentation, it is still not very much developed. It is under development. And enzyme method it is not that popular because it is a expensive method. So from fermentation, we can get ethanol. In anaerobic digestion, we get methane and biogas, and from enzyme, we get ethanol and amino acid. But this enzyme route is not widely used because it is very expensive. Then the second one is chemical conversion, which includes hydrolysis, solvent extraction. These methods, we will also be talking about them. Then trans-esterification, mainly we will be talking about trans-esterification. Then physical method include mechanical extraction, briquetting of biomass and distillation. So here in this, we will be basically talking about this, which is the mostly used, which is briquetting of biomass, and what is physical conversion, that also we will be studying further. Now coming on to, as I told, we will be talking about the anaerobic digestion, which is a biological conversion method. So anaerobic digestion, it includes the feedstock which can be used for anaerobic digestion. As I told that if the moisture content is very large, very high, then we mostly employ anaerobic digestion. So in that, feedstock is basically energy crops, animal waste, industrial waste, then municipal waste, MSW is municipal solid waste, then restaurants and food industry waste, then sludge from wastewater treatment plant, etc. They all come under the feedstock, which can be treated in anaerobic digestion. So it is basically what is done biological in this microorganisms break down the biodegradable material in the absence of oxygen. So this is basically anaerobic digestion. Anaerobic means in the absence of oxygen. So whatever takes place, this method, it takes place without the presence of oxygen. And main products, what we get is the biomass, then hydrogen also we get, then bio fertilizer, compost, and reusable water. Coming on to the steps. So what are the basic steps which are involved in anaerobic digestion? AD is anaerobic digestion. This AD, it is anaerobic digestion. So basically our feedstock is all components, they mainly consist of what? Complex organic components, basically carbohydrates, fats, and proteins. So first step is hydrolysis. Pre-treatment is done, which involves hydrolysis of these complex organic compounds or feedstock. Then by using hydrolytic bacteria or enzyme, different kind of bacteria are used, which we will be studying further what kind of bacteria are used in each step. When we do the hydrolysis of this chemical organic compounds, it converts into simple organic compounds, which are basically sugars, amino acids, or peptides. Then acidogenesis takes place, which is done in the presence of fermentative bacteria. Basically, these larger molecules are converted into short chain fatty acids. And then the third step is acetogenesis. This is acidogenesis and this is acetogenesis. So understand the difference. We will be talking further what is the difference basically. So acetogenesis, what happens is short chain fatty acids are converted into this acetic acid or hydrogen and carbon dioxide using hydrogen produced. This is done by acetogenesis procedure, and this is done by hydrogen producing acetogenic bacteria. So some amount of sometimes acetic acid can also be formed, or we can get hydrogen and carbon dioxide. So and further in the methanogenesis procedure, this acetic acid is converted to carbon dioxide or methane, and here also this hydrogen will also be converted to methane or carbon dioxide using methane producing bacteria. Reactions, we will be talking further what kind of reactions are taking place. So this is a short table type structure which tells us that how anaerobic digestion takes place step by step. Coming on to the quantitative description. So basically we have seen that here organic compounds, the first one, this organic compound here, this organic compound when converted to short chain fatty acids, mainly if it is done directly, then only 76% conversion is there. And if it is this organic compounds are sometimes directly converted to hydrogen, then only 4% conversion is there, is noted from directly from organic compounds to hydrogen by hydrolysis and acetogenesis. Simultaneously, if hydrolysis and acetogenesis takes place, then only 4% conversion is there. Therefore, we are mostly trying to convert them step by step, firstly to short chain fatty acids, and then from short chain to hydrogen and acetic acid. As we have seen that the conversion is more in two-step reaction. But directly, if we do, then the conversion is less, that is for 4% and 20%. And then this hydrogen is converted to methane, which is about 28%, and acetic acid to 72% by the acetogenesis and dehydrogenation and methanogenesis procedure takes place here from hydrogen to methane. Now, elementary description of anaerobic digestion. In the case, the chemical composition of the organic matter is known. The stoichiometric equation according, this is a basically an empirical equation which is given by the scientist McCarthy in 1991. He gave that if suppose this is our feedstock, then it reacts with water, and basically this water consists of some kind of microbes and microorganisms which reacts with this feedstock, this biomass. These microbes reacts with this biomass to give CO2 in this biowaste, this biomass, and then ammonia and SCO3 negative. So it is basically an empirical formula which was given. So basically, if we can know that we can calculate N, A, B, C, etc. all using the stoichiometric formula of our feedstock, which will be given. And S and E is basically the fraction of waste converted into cells and fraction of waste converted into methane for energy. Now let us talk about the about all these steps in detail. This hydrolysis, acetogenesis, and methanogenesis. We will be talking about them in detail. So, firstly, is hydrolyzing and fermenting bacteria. So, these obligate anaerobes, the various bacteria which are used in the hydrolysis steps are basically bacteroids, Bifidobacterium, Butyrosvibrio, Eubacterium, and Lactobacillus. They basically act as acidogenic bacteria. So the product, as we have seen here, the product after hydrolysis are sugar, amino acid, and peptides. So basically, they are given here in detail. What we get mainly sugar, some kind of alcohol, then amino acids, ammonia, sulfides, CO2 and H2, and glycerol. So many enteric coliform bacteria classified, represented by the pathogen Escherichia coli in the genus Escherichia, and pathogens in in the genera Salmonella and Shigella are also some common fermentative bacteria. So they are basically acidogenic bacteria, and conversion during acidogenesis we have seen here that after acetogenesis we get these short chain fatty acids. So that is what here it is told in detail. That's what kind of fatty acids are formed. We get succinate, acetate, propionate, lactase, formate, etc. And some amount of carbon dioxide and hydrogen. So all this we get. Now coming on to acetogenic bacteria, basically here we can see acetogenic, it comes from the name itself. It is the conversion of short chain fatty acids to acetic acid. Therefore, it is acetogenesis. And here these sugar molecules are converted to acids, fatty acids. Therefore, it is acidogenesis. So hydrogen producing acetogens are basically, as we have seen, that during acidogenesis we get different kind of products such as propionate, lactase, formate. So all these are further converted to acetic acid or hydrogen by acetogenesis. Therefore, hydrogen producing acetogenesis. This propionate on reaction with water gives acetic acid, and here this propanol on reaction with water gives acetic acid. and then butyrate on reaction with water gives acetic acid. So it is basically acetogenesis reaction. Here we get acetic acid. So these reactions takes place in acetogenesis is step, and the bacteria used are Clostridia and Aceti vibrio. And another is homoacetogens, in where this hydrogen and carbon dioxide reacts to give acetic acid. So these reactions basically takes place collectively in acetogenesis step. Then methanogenesis, the various bacteria, two different types of bacteria are used in methanogenesis step, which is acetoclastic methogens. When acetic acid is converted to methane, our main target is the methane, but sometimes we also get some amount of carbon dioxide. And the second type is hydrogenotropic methanogenesis, where hydrogen is on reaction with carbon dioxide gives methane and water. So 70% of methane is used by this route. They are highly sensitive and have slowest growing rate. So this one is, we get 70% of methane from this step, and 30% of methane is produced by the this one step. They are less sensitive and have higher growth rate. And sometimes we also have formic acid and methanol can also be in our biomass. If some amount of formic acid and methanol is also present, then that can also be converted to methane by this reaction. So methanogenic bacteria are basically unicellular gram variable strict anaerobes that do not form endospores. Their morphology, structure, and biochemical makeup are quite diverse. And they are basically divided into three different groups based on the fingerprinting of their 16S ribosomal RNA and the substrate used for growth and methanogenesis. So, group 1 contains genera Methanobacterium and Brevia bacter, and group 2 consists of Methanococcus, and group 3 contains genera including Microbium, Methanogenium, and Methanospirillum, Methanocercina. Now coming on to the flow sheet for anaerobic digestion of waste. So this is basically a flow sheet which according to which anaerobic digestion of biowaste takes place. So firstly, what we will be taking, it is the organic waste, basically the organic waste, and some amount of water and chemicals will be introduced for shredding, blending, for basically reducing in the size. Shredding will be done, then its mixing, blending will be done, and pH adjustment will be done. So here, or after all this, pre-treatment of feed will be done, and then it will pre-treatment basically involves, if suppose some kind of heavy metals or pH maintenance is not there, then anaerobic digestion will not take place. Therefore, all the just a second. Hmm. So if some kind of pre-treatment is required for pH maintenance or for removing some kind of heavy metals or some kind of impurities are there, so pre-treatment is done. Then it is sent to the anaerobic digestion digester basically, where anaerobic digestion takes place, and we get the mixed gases from above, which may contain methane, water, acid, and some gases some other gases such as carbon dioxide and hydrogen sulfide. And then the gases are given from above, and the sludge is given from below. It comes to the dewatering, where if it consists of that sludge consists of water, then this water is sent back here. Then and sludge is sent for the disposal from below, and after dewatering, if some liquid or water is there, then it is sent to this treatment unit for further, either we can recycle it back here or we can use it for other purposes after treatment. So anaerobic digestion is also two types basically of dry waste and then wet waste. So if we do the anaerobic digestion of dry biomass and wet biomass, what is the difference? So total solid content will be more in dry anaerobic digestion compared to the wet one, as we can see here. And the reactor volume in case of wet, it is required more. More reactor volume is required. And treatment of this wet anaerobic digestion, it is solid liquid separation is expensive in this case compared to dry. Then energy balance here, it is more improved compared to wet, and economic performance is also better in case of dry anaerobic digestion. Then retention time is shorter of dry anaerobic digestion compared to the wet, which is quite more than the dry anaerobic digestion. And the type of feedstock accepted here in dry anaerobic digestion, any kind of feedstock we can use. There is, we can flexibility of feedstock is there, but in case of wet, it is not that flexible. Coming on to the kinetics of methane production. So, methane, mostly the rate limiting step in methane, one of the steps might be rate limiting steps among the steps, as we have studied that there are four steps. That is the first one, hydrolysis, acidogenesis, acetogenesis, and methanogenesis. So mainly the methanogenesis is the rate limiting step, but it is not a hard and fast rule that always methanogenesis will be the rate limiting step. If the cellulose content is higher, then hydrolysis, that complete hydrolysis will not take place. It will be very slow. So sometimes, so then in that case, hydrolysis can be the maybe the rate limiting step. If there is a presence of lignin, which decreases the rate of hydrolysis. So if hydrolysis is the slowest step, then it will be the rate limiting step. And the transfer of gaseous product to the gas phase may be also be the rate limiting step. So mainly we have seen that methanogenesis is the rate limiting step, but it is not fixed. Matlab basically, during the experimentation, sorry, during the treatment, it may vary depending on the conditions. Which step is the slowest step? That will be the rate limiting step. So it is a theoretical equation is given for the kinetics of methane production, which is R equals to S naught into mu max theta minus 1 minus Ks upon theta into mu max theta minus 1. So here R is the substrate converted for liquid volume at hydraulic retention time theta. So theta is the retention time, R is the substrate converted per volume. Then S naught is the substrate concentration in the feed. And mu max is the maximum specific growth rate. Ks is the saturation constant or substrate concentration at which the specific growth rate is half mu max. So basically at 30 to 37 degrees C, optimum conversion of glucose can be achieved at theta of 4 hours and 4 days in the acid and methane phase reactor. So here it is basically an example given that if anaerobic digestion is taking place in this temperature range, then the retention time will be a conversion of glucose retention time is 4 hours, and acid and methane phase reactor mean the methanogenesis step takes place 4 days. So for so here the value for mu max and Ks for acetogenesis of glucose and cellulose are given, and methanogenesis of acetate is also given. They are basically the experimental values used for this example. The example given here. So this is the example given of methanogenesis of glucose, and this is acetogenesis of glucose and acetogenesis of cellulose is given. And different retention times are also given, as we can see here that acid phase digestion here takes place 1 or 2 days, whereas the methanogenesis step takes place 5 to 8 days. So for these two examples, the value of mu max and Ks, that is the saturation constant, is given here. Now coming on to the types of anaerobic digesters, they are basically two types: the low rate anaerobic digester and high rate anaerobic digester. The low rate, it is basically intermittent mixing, sludge feeding, and sludge withdrawal. So retention time is very large in the low rate. As we can see, low rate, that means it is taking place very slowly. So for very large, for more number of days, detention time here is very is more than compared to the high rate, which is almost less than 15 days. So feeding rate is zero point 0.5 to 1.5 kg Vs per meter cube day per day, and feeding rate here is more than this one. As it is high rate, then it can convert more feed compared to this in a same uh, in fixed time. That is, if suppose we are doing the using both the digesters for a single day, then the feeding this high rate can convert more amount of feed compared to low rate. So most digesters are heated and operated in the mesophilic range and usually made of concrete or steel. It is told that digesters, they are mainly made of concrete or steel. Digester operation, most digesters operate in the temperature range. Basically, the optimum temperature range for operation of these digesters is 30 to 38, and the digester gas produced from the process may be used for heating purpose. pH maintenance is also very important in case of anaerobic digestion. So the optimum pH should be pH range is 77 to 7.2, maintained by properly seeding fresh added sludge and not excessively withdrawing sludge. So basically, different methods are used to maintain this pH range. Either we add fresh sludge regularly at regular intervals and not excessively withdrawing sludge. So temporary solution for acidification is lime addition. So if suppose the temporary solution for acidification, that means if acidification takes place, then its pH will decrease. It will not be in the same range. So for that purpose, lime addition is done sometimes to maintain this pH. And heavy metals may inhibit digestion process. So if there are some kind or some amount of heavy metals are present, then they need to be eliminated at the source itself. Mean during the pre-treatment step, as I told, that if some amount of heavy metals or something are present in the in our feedstock, then it should be eliminated. The supernatant liquid is the water released during digestion. Some during the sludge, when bio sludge is given out, as we can see here. Then here some bio sludge is there. Then it consists of some kind of supernatant also. That means that supernatant is basically water. May have BOD as high as biological oxygen demand. It is basically as high as 2000 milligram per liter, and SS concentration as high as 1000 milligram per liter, fed back to the effluent to primary clarifier. So this supernatant liquid, it is basically water. Either we can recycle it, either we can treat it and use it for different other purposes, or we can even recycle this water back to the digester. I mean, during the pre-treatment, as we have seen that we need to introduce water here. So either we can recycle this water back here, or we can discharge it and use it for other purposes also. So there are basically two type of digesters: one single stage and two stage. So two stage has better overall gas yield. Why that so? Because in a single phase digester, optimum pH which is maintained, as we have seen here, it is given 7 to 7.2. So the optimum pH in single phase digester is 7. But there are two types of reactions taking place. Acidogenesis reaction is taken place in the pH of 5.5 to 5.9, whereas the methanogenesis takes place at higher pH, that is 7.4 to 7.9. So if we take a single stage, then the pH is maintained only 7, which favors only methanogenesis reaction. So acetogenesis reaction will be hampered. So that's why there is less conversion. So if we instead of using single stage, we use two different steps. So maintaining this pH in one digester and this pH in second digester, this will basically favor both the acidogenesis reaction and methanogenesis reaction, and we will be getting better gas yield. So here, simply what we will be doing, feed will be given, and here acidogenesis will take place at 5.5 to 5.9 pH, and then we can guess some amount of gas here, mainly that is methane, and sludge will be given out from below, and further it will be sent to second digester where the pH is maintained from 7.5 to 7.9. There also we will get the gas from above. Then this supernatant is basically, we have told it is water. Supernatant is removed from above, and this sludge is given out from below. Supernatant is taken out from this side. So as we can here see, the two-phase reactor improves the overall gas yield. Now coming on to the second lecture, which includes the chemical route. Till now we have studied the biological route, and now this is the chemical route, which involves transesterification process. So basically, what is transesterification? In this, what we do, an alcohol reacts with the triglyceride oils. So these are basically the triglyceride oils, which are mainly the plant oils, the oil we get from plants. Why triglycerides? Three, as we can see, this glycerol consists of three OH. It is called glycerol. So here also three esters are present. So they are basically called triglyceride oils, which are mainly derived from plant oils, animal fats, or recycled grease to form fatty acid alkyl esters. So these are basically they are converted to fatty acid alkyl esters. This plant oil is converted to fatty acid alkyl esters by its reaction with methanol or some kind of alcohol. It is not necessarily only methanol. It can use any alcohol such as methanol, ethanol, etc. When this plant oil reacts with this methanol, what happens? It replaces this CH2, CH and CH2 with this methyl group from methanol. It is replaced. Here also methyl group comes, here also methyl group, here also methyl group. So we get different kind of fatty acids of methyl esters. Either they may be same or they may be different. So we get this and all this is done in the presence of a catalyst. Basically, some a strong base catalyst such as NaOH or KOH. That kind of catalyst is used mainly. And along with the fatty acid methyl ester, we get glycerol. So this is basically the biodiesel part. So organic waste for transesterification is taken. What happens is, if suppose we have this waste seed oil, so what happens is this transesterification basically is these plant oils, they are basically lipids. These plant oils, they are basically lipids or lipids and oils. So these if the organic waste is waste oil seeds, then firstly we will have to extract oil from them. That is the bio oil we have to extract from them, and then this bio oil is transesterification takes place and converted to biodiesel. And if some kind of waste oil or cooking oil is there, that can also be uh, converted to bio oil. And if some amount of recycled grease is there, that can also be converted to biodiesel. Some other routes for energy production are some other chemical routes are such as incineration, gasification, pyrolysis, anaerobic digestion. So all this we have studied earlier, this gasification, pyrolysis, all this we have studied during coal energy production, and this anaerobic digestion just now we studied. Just a second. Now coming on to the this is basically the production of bio oil from oil seeds. So there are different methods of production of, as we know that firstly we need the for transesterification. The reactant is basically in the oil form, basically lipids. So firstly, we have to convert, if we don't have our organic waste in the oil form, then firstly we will be converting it to oil, then transesterification will be done. So basically, these are the different methods of uh, extracting oil from the oil seeds. So the conventional method include the expeller press method and the solvent extraction method, and the advanced method includes the ultrasonic assisted extraction and supercritical fluid extraction method. So expeller press is basically simply by crushing or in applying pressure on the oil seeds, we can get oil. That is the conventional method, simple method. And the solvent extraction is basically dissolving these oils by using some kind of solvent. If suppose we have our crushed oil seeds, then if we mix them with some kind of solvent which can take this oil part along with it and leaving the slurry, the solid slurry of the oil seed waste behind. Then ultrasonic assisted extraction also, by using ultrasonic waves also we can mean what we do is we if we sonicate these oil seeds, ultrasonicate these oil seeds, the that solid part gets separated from the oil part. And the supercritical fluid extraction method, in this we use supercritical carbon dioxide for the extraction of this oil from the oil. So, coming on to why upgradation is required. Why can't we use this plant oil as it is? So, the reason for that is this plant oil is much more viscous compared to the conventional diesel fuel. So, it is almost 11 to 17 times thicker compared to this diesel. Okay. So, this plant oil has very different chemical properties, and also this plant oil has very different chemical properties and combustion characteristics compared to conventional diesel fuel, which we use in our vehicles. So if the fuel is too thick, that it then it will not atomize properly when the injectors spray it into the combustion chamber, and it will not combust properly. So due to this viscosity, it will not combust properly into the engine, and the injector may get choked, leading to poor performance, higher exhaust emission, and reduced engine life. So basically, thickness reduction is the requirement, and the waste oil, cooking oil, and recycled grease lose their properties. Mean this waste oil, cooking oil, and recycled grease, they have already lost their properties. So some kind of recycling is required to uh, replenish its properties to be used to use them as biofuel. And the transesterification improves the quality of these feedstock and impart fuel properties. So basically, the aim of this transesterification is improving the quality of these food stocks to impart fuel properties to them. That is basically to get the biodiesel. So generalized flow sheet for biofuel production from various feedstock is basically we have this vegetable oil or recycled grease as feedstock, as we have studied earlier. So this vegetable oils are basically they are directly sent to the transesterification chamber, but this recycled oil needs to be pre-treated. So what is this dilute acid esterification? Why this is required? It is basically this recycled grease consists of large amount of free fatty acids. So these free fatty acids, if the percentage of this free fatty acid is very large, then they will transform into two soaps using this NaOH or KOH catalyst. These free fatty acids will form soap, thus will hamper this transesterification reaction and formation of biodiesel. So to remove these free fatty acids, we introduce alcohol and H2SO4 here to remove this free fatty acids. So pre-treatment is done here in dilute acid esterification. These free fatty acids are removed from recycled greases, And then after this pre-treatment, it is sent to the transesterification reactions. And this vegetable oil, they don't have high amount of free fatty acids. Mainly, some amount it consists, if, but if there 4% or less amount of free fatty acids are acceptable, but more than that is not acceptable. So in vegetable oil, if free fatty acids are are present also, then they are present in very less amount. But in case of recycled greases, free fatty acid percentage is very high, so pre-treatment is a must, which is done in the dilute acid esterification. Then here transesterification takes place in the presence of alcohol, basically methanol, and catalysts such as KOH and NaOH. And then this after transesterification separation is done here as we have seen in the reaction. We get two different components. First one is the biodiesel component, which basically i- this part, the fatty acid methyl ester part, and then the second part is the glycerine part. So here biodiesel refining takes place if some amount of water or anything is present, then it will be and if some acid is present, then it will be recycled back here for pre-treatment of recycled greases, and refined biofuel will be given from here. And if some kind of alcohol is present, some may be recycled here, some may be recycled here also. And in glycerin also, after refining, it is given here the refined glycerin. And if some amount of alcohol is present, then that will be recycled back to the alcohol recovery to use it here in again in the transesterification reaction. Now the coming on to the steps for upgradation. So basically it involves five steps. The first one is acid esterification, then the trans esterification, then the methanol recovery, biodiesel refining, and glycerine refining. So basically coming on to the acid esterification, which is basically the pre-treatment steps for this filled grease. And why so? It consists of free fatty acids, large amount of free fatty acids. So firstly, we will talk about acid esterification. So basically, it there are various methods to remove these free fatty acids. The first one is basically the enzymatic method, but as I told, enzymatic method is very costly, so it is not a popular choice. Then the second one is glycerolysis, where glycerol is added to high free fatty acid feedstock. That is basically if suppose we have a recycled greases, as I told, it consists of high free fatty acids. So if we have a feedstock containing high free fatty acids, then glycerol is added to it with catalyst ZnCl2 at 200 degrees C, which converts the free fatty acids to monoglycerides and diglycerides plus water. So this can also take place. Water is vented as it is formed and this method require high temperature and it is a slow process. Acid catalysis followed by base catalysis. This can also be done. Acid catalysis for conversion of free fatty acids to methyl esters. Firstly, this free fatty acids will be converted to methyl esters until this free fatty acid content comes under 0.5%, followed by addition of methanol and base catalyst to finish the reaction. So, firstly, acid catalysis will take place, which will convert it to methyl esters, and then methanol and base catalyst will be added to finish the reaction. Acids such as H2SO4 catalyze both esterification and transesterification reaction, but esterification of free fatty acid is fast. It takes place within an hour, but transesterification is slow, that is, takes up to 2 days at 60 degrees C. So here basically it is told that both steps are done in the single step. This acid esterification and transesterification here takes place in a single step. Mean if we use heterogeneous catalyst, it is basically heterogeneous catalyst system where we are using two different kind of catalysts. First one is the acid catalysis for conversion of free fatty acids to methyl esters, so that to eliminate the formation of soap, it is converted to methyl esters. And then base catalyst is used for transesterification reaction. Base catalyst, that is mainly what we use, which is methanol, and base catalyst, which is NaOH. Here we have seen we use it for transesterification. So basically, both first steps, acid esterification and transesterification, are taking place here simultaneously. Now, conversion of Free fatty acids can be determined from the following equation. S naught is the initial value, initial acid value, and Si is the acid value at some reaction time upon initial time. So this is basically the conversion. Determination of acid value, known amount of sample is added to some amount of neutralized ethanol and is fully dissolved by heating. Phenolphthalein is added as an indicator. The sample is then titrated with standard potassium hydroxide solution. So the acid value is calculated as S equal to 56.1 into V into C upon M. So basically S is the acid value. We can calculate the acid value from this formula, that is milligram of potassium hydroxide per gram of waste cooking oil. C is the concentration of potassium hydroxide used for titration. This and V is the volume of KOH employed for titration, and M is the mass of the sample taken for analysis. Now coming on to the second step, which is transesterification. So basically the plant oil which contains less than 4% free fatty acid is first filtered and then pre-processed to remove water and other contaminants. As I told that if free fatty acids is less than 4%, then there is no such problem. We can use it without removing it. So because 4% is very less, so formation that will not hamper our transesterification reaction. So if it is less than 4%, then directly we can filter the our plant oil to remove some amount of water or if other impurities are present. Then this pre-treated oil is then fed directly to the transesterification process along with any product of the acid esterification process. So basically it is telling this portion is less in free fatty acids. So here acid esterification is not required, but as we have seen here, this here consists less than 4%, it is directly sent here. But if some other consists of more free fatty acid, then it is after pre-treatment sent along with the transesterification, sent along with this plant oil to the transesterification process, which is told here. The catalyst potassium hydroxide is dissolved in methanol and then mixed with the pre-treated oil. Heterogeneous catalyst can also be used. As I told, heterogeneous catalyst, it will improve the performance of the transesterification reaction. If an acid esterification process is used, then additional alkaline catalyst must be added to neutralize any excess acid remaining from that step. So, if acid esterification was used, as we have seen in the case of recycled grease, if let me come, this acid esterification is taking place, if it is done in some with some feedstock, then also we will have to add extra KOH here, extra alcohol here, so that if then also some kind of free fatty acid are remaining even after dilute acid esterification, then that can be neutralized here and would not hamper the transesterification reaction. Once the reaction is complete, the two major co-products, biodiesel and glycerine, are separated into two layers. When the second, then third part is the methanol recovery. The methanol is usually removed immediately after the biodiesel and glycerine have been separated. This is done to prevent the reaction from reversing itself. Recovered methanol is cleaned and recycled back to the beginning. So as we have seen here, in both the step, immediately methanol recovery takes place. This alcohol is basically methanol recovery takes place in both the steps. Biodiesel refining, once separated from the glycerine, the biodiesel goes through a series of cleaning or purification steps to remove excess alcohol, residual catalyst, and soaps. These consist of multi-stage washing with clean water. The product biodiesel is then dried and sent to storage. It can be further refined through an additional distillation step to produce colorless, odorless, zero sulfur, or premium quality biodiesel. When coming to glycerine refining, the crude glycerine from the transesterification process may be recovered or used in a fuel blend for steam production. The crude glycerine contains unreacted catalysts, so that must be neutralized with acid. The water and alcohol are also removed, produce 50 to 80% crude glycerine. We get mainly 50 to 80% crude glycerine. The remaining contaminants include unreacted fats and oils. In large biodiesel plants, the glycerine can be further purified through a series of unit operations to produce a product of 99% high or higher purity. This purified product is suitable for use in various pharmaceuticals and cosmetic industries. As we know, glycerine is used in various pharmaceutical in various medicine as well as in pharmaceutical industry. Now coming on to the third part, which is densification. As I told that the third part would be the physical route. So what is basically physical route? It is basically the transformation or treatment of our biofuel in such a way so that we can make it in a way that it is easy to handle and to basically easy to handle, easy to transport and feeding in the reactors, etc. That becomes easy. So basically, the first thing in physical method is densification. So what is densification? It is basically increasing the density of something. It makes a fuel denser and gives more uniform properties with respect to its raw form. So as we know that basically if we take the biomass, it is mainly straw or cow dung, etc. They are very mushy because it consists of large amount of moisture. So we just want to increase its density so that it is easy to handle. So different steps which can be used for densification is the compaction, compression, concretion, or concentration, and which we will be studying further. So advantage is simply mechanical handling and simplified mechanical handling and feeding, uniform combustion in boilers, reduced dust production, reduced possibility of spontaneous combustion in storage, simplified storage and handling infrastructure, lowering capital requirement at the combustion plants, reduced cost of transportation due to increased energy density. The only disadvantage with this is that by to is the high cost associated with some of the densification processes. So densification fundamentals basically involves the densification of biomass under high pressure results in mechanical interlocking and increased cohesion and addition of the solid particles which forms intermolecular bonds in the contact area. So basically different techniques used for densification is adsorption layers, hardening binders. If we can use some kind of binders also for increasing their density, then molecular forces, van der Waals forces, then interlocking can also take place. Electrostatic forces can also help different particles of biomass to bind together. So now densification, when the particle is compacted with low to moderate pressure, then the space between the product particle is reduced. If suppose we have many different particles, if we apply pressure, suppose we are pressing them, this is a base plate, this is an upper plate, and here we have our biomass. Suppose these are different particles. And if we apply pressure here, then these particles, the space between these particles will decrease. If the pressure is increased at a certain stage particular to each material, if this pressure goes beyond a threshold value, then the cell walls of the cellulose constituents can collapse. Then the pressure required to achieve such high densities are basically the threshold pressure required to achieve high density is basically 100 megapascal or more than that, and the binding agent is necessary to prevent the compressed material from sprinkling back and eventually returning to. Sometimes some kind of binding agents are also used because if we remove this pressure, so that when we remove this pressure, all these particles may not detach again, may separate again. Additives of high viscous bonding media uh, mainly binding agents or additives such as tar, molasses, and other molecular weight organic liquids can be used to bind to form bonds very similar to solid bridges. Just a second. Additional forces at the solid liquid interface and cohesion forces. So if different phases are there, then there is addition forces, and if same phase is there, then cohesion forces are there, which are used for the binding. And the binding agent can either be added to the process or when compressing ligneous materials, be part of the material itself. Means sometimes we can add binding agent also, or sometimes if there is, if the lignin amount is more in our biomass, then that lignin also sometimes act as the binding agent. So then we don't need to add binding agents from binding agents externally. So the resulting solid is basically it is called briquette. If roughly it has a diameter greater than 30 mm, so these are briquettes basically, and they have diameter greater than 30 mm. And if smaller sizes are there like this, then they are basically called the physical properties. That is, physical properties required are the moisture content, bulk density, void volume, and thermal properties of the biomass are the most important factors in the binding process of biomass density. Mean the in densification, if we have to check what some properties we have to check, such as what amount of moisture contained, it also affects the densification. Bulk density affects the densification, then void volume, etc. And the ultimate density of a briquette will depend to some extent on a range of factors. Most importantly, the nature of the original material and the machine used and its operating conditions, as well as minor factors. So types of briquetting, it is basically three types: high pressure compacting, medium pressure compacting with device, and low pressure compacting with a binder. So if high pressure compacting is basically pressure to 5, pressure of 100 megapascal or more. When very high pressure we apply, then sometimes we don't require any binder or heating device directly due to high pressure. These biomass gets densified and uh, mean without sprinkling back to its original state. Then if we reduce the pressure a bit, that is the medium pressure, then sometimes some amount of heating is required. The intermediate pressure is 500. If we apply pressure of 5 to 100, between 5 to 100 megapascal, then medium pressure is applied and some amount of heating is also applied, so that the after removal of this pressure, the biomass particles do not sprinkle. Just a second. And in case of low pressure compaction, some amount of binder is required, because in low pressure compaction, we don't apply very high pressure. That is, pressure up to 5 millipascal is only applied. So for proper binding and proper binding without sprinkling back of these particles after removal of this pressure, some kind of binder is used. Usually, high pressure processes releases sufficient lignin to agglomerate the. During high pressure processes, what happens is they release some amount of lignin. This biomass release lignin, which act as the binder. So externally, binder is not required. In case of intermediate pressure machines, may or may not require binders depending upon the material. And low pressure, invariably, basically, they require binders. Two different types of machines we will study about, which are used in briquetting. Basically, formation of these dense biomass. So piston presses. This is basically a piston press, which here we introduce our biomass, and it goes down below, and this piston applies pressure here. It goes, I mean, in this direction. When feedstock comes from here, it is settled here, and this is pressed from here. When this applies pressure, it forms a briquette here. Presses plunge the feed material into a die with very high pressure, either mechanically by a reciprocating ramp powered by a massive flywheel or by a hydraulically driven piston. The mass is compressed and forms a very dense liquid. So this is basically a piston press. Now coming on to the second machine, which is the screw press. So what happens is we introduce our feedstock here, and the rotating screw here takes the material to the feed port through the barrel. Through this barrel, the feedstock goes, and it is compact it against a die. Here, this is the die, and it is compacted against this die, which assists the building of a pressure gradient along the screw. It consists of three zones. First one is the feed zone, then this is the transport zone, and this is the extrusion zone. So we will get our briquette from here. So this is the die. We will get this shape of liquid from here. Screw press and screw extruder, basically the performance of the process depends on the flowing ability of our biomass material and the cohesion of the feed material, particle size and distribution, surface forces, adhesiveness, etc. This affects the formation of our briquette. Screw presses provide high quality briquettes with a homogeneous structure and good combustibility. Requires only little maintenance. Only disadvantage is the wear of the screw leads to elevated spare part. Important briquetting process. Two types binding agents, two kinds of binders are used in briquetting: the organic binders or inorganic binders. So organic binders involve bitumens or molasses, starch, coal tar, or resins, and inorganic binders involve cement or lime, clay, or sulfite liquor. During the compaction process, the briquettes are brought into shape without giving them substantial strength after subsequent curing. So, if we apply this binder, then they are not given a proper shape. Firstly, only binder is applied, a small force, binder is added, low pressure is applied, and after that, a subsequent curing step, that is drying, burning, or chemical reaction takes place, and the green liquids are developed with the required strength. Coming on to the carbonization process. So, what is basically carbonization? When we form these briquettes, they are basically, as we have just just a minute. So, so what is carbonization? So basically, as I have told, that biomass consists of large amount of moisture content. So during this briquette formation, also moisture content is present. So to increase the heating value of our liquids or our biomass, this carbonization procedure takes place. So what happens? Although briquettes can be used directly as fuel, the burning of the briquettes has some demerits. It increases the generation of smoke. If uh, moisture content is more, then generation of smoke will be there. Reduced ignition and burning properties, low heating value, not stable under wet conditions. So carbonization is partially pyrolysis process where it is heated up to 600 degrees C, and burnable gases like carbon monoxide, methane, hydrogen. Just a second. Just give me a minute. कौन कौन Sorry for the interruption, guys. Okay. So where we were. So basically, what happens in carbonization? It is basically partial pyrolysis takes place where it is heated, where these briquettes are heated up to 600 degrees C, and burnable gases such as carbon monoxide, methane, hydrogen, formaldehyde, ethanol, formic acid, and acetic acid, as well as some non-burnable gases such as carbon dioxide and water and liquid tar are released. So due to above reasons, carbonized liquids overcome all other. So after carbonization, what happens is all these demerits are overcome. The change of the properties due to carbonization, how change of property takes place if suppose this is pine needle and this is pine needle char and this is pine needle briquettes. So we can see that ash content is increased. Obviously, after heating, ash content will increase. Moisture content is reduced. We can see from 9.76 to 7.5, then to 6.89. And the volatile content we have seen is decreased considerably from 17 and then it has increased some to 29.04. And the carbon content is also increased compared to original, nascent form of pine needle. So it is not this briquetting. It is not necessary that after that pine needle is firstly carbonized and then briquetting is takes place. It can also take. It can also occur that pine needle is firstly converted to briquette and then it is then carbonization is done, or either this pine needle first carbonization is done and then briquetting is done. So there is no such hard and fast rule that we have to do briquetting first only then carbonization, or carbonization first only then briquetting. Now, this biomass part is over. So let us move to our concluding part, which is basically energy conservation. So as we have seen that nowadays we just want to conserve energy for various reasons such as sustainability reasons, then to reduce carbon emission, to reduce to reduce pollution and global warming, etc. So the need of the hour is energy conservation. So basically, we have seen various forms that if we replace these non-renewable energy sources to renewable energy sources, then we can then we can do the energy conservation and we can save these means we can eliminate carbon emission and sustainable goals can be reached. But there are some, not only these methods are there, some rules and regulations are made uh, in the society as well as by the government so that we human beings can simply do such small things, small efforts to do the energy conservation. So basically, we will be talking about some about that energy conservation for efficient use of energy. So basically, energy conservation refers to the efforts made to reduce energy consumption. It can be achieved through increased efficient energy use in conjunction with decreased energy consumption or reduced consumption from conventional energy. Basically, individuals and organizations that are direct consumers of energy choose to conserve energy to reduce energy costs and promote economic security. Energy conservation is often the most economical solution to energy shortage. Basically, in India, government has passed an energy conservation bill in 2001 for better utilization of energy and conservation of the same. By this act, it is mandatory for energy intensive sectors to get their energy audit conducted by energy auditors. Bureau of Energy Efficiency. This body keeps watch on energy consumption patterns and develops norms for appliances. And star ratings, as we all know, that different electronic gadgets have different star ratings. So, Bureau of Energy Efficiency has also initiated star rating system for electrical appliances such as CFLs, geysers, refrigerators, etc. So, energy conservation at community level for housing complexes. Either we can do installation of This is basically that theory part. So, I will be reading it out. Installation of photoelectric controls or timers should be used, as we can see in many buildings and many offices nowadays. Sensors are employed for that lights. That if somebody is there in the room, then only light will be on. Otherwise, it will be off. So all such measures can be taken even at our homes. We can take such measures. Water pumps should be switched off during non-peak utility hours. During non-peak hours, water pumps can be switched off. Then, if there are numerous lifts, then only one or two lifts can be functional during non-peak hours. That may uh, that will help in conservation of energy. Then training programs about energy efficient repairs should be organized. Locally manufactured, improved cook stoves should be introduced to reduce charcoal fuel consumption. Then energy conservation in transportation sectors, reduction of fuel consumption, car speed should be maintained as far as 50 to 60 kilometers per hour. We should avoid frequent starts and stops to reduce fuel consumption. As we know, during start and stop, fuel consumption is more, so we should avoid frequent start and stop of the engine. Then we should apply brakes gradually as far as possible. Then fuel economy, moderate driving, then driving at low speeds, turning off a vehicle engine at stops rather than idling and using cruise control. And sometimes carpooling can also be done. All these things will uh, reduce the energy consumption. Then energy conservation during lighting. There are two methods. Selection of lighting in buildings. Two methods are available: building areas method and space by space method. So building area method is discussed here. It is basically the interior lighting power allowance by the building area method is determined in accordance with the following. Determine the allowed lightning power density. Allowed lightning power density, it is basically a table is given for different building areas, such as for the living room, for the garage, for office buildings, for that bathrooms, and then toilets. Different lightning power density is given. There is a table given. Okay, forgot to add it. So from that, different areas have different lightning power density LPD value for different areas of a building are given in that table. From there, we can take. Suppose we have a place, we have a house. Suppose there are two rooms. Suppose two rooms are there. One garage is there. Three washrooms are there. Then one kitchen is there. Suppose. Then LPD value for all these areas is given in a table. We will take that value. Calculate the gross lighted floor area for each building area. We will calculate the gross area in the lighted areas. If suppose light of one room is not on, so we will be taking LPD 1 only. We will not be multiplying it by 2. And then in the interior lighting power, sorry, gross lighted floor area, we will be taking the floor area of one room only. Suppose three washroom, only two are in continuous use. Third one, we don't use much. The lightning is not on, so the area of third one we will not be taking. So likewise, this gross lighted floor area for each building area. So the interior lighting power allowance, that is ILPA, is the sum of the products of the gross lighted floor area of each building area times the allowed lighting power density for that building area type. So this is the formula basically. We will be multiplying this area into LPD value of each place, each lighted place, and then adding it all. So this can be done for energy conservation during lighting. Energy conservation in industries through motors. So electric motors converts electrical energy into mechanical energy. Energy can be saved by using energy efficient motors in place of standard motors. Energy efficient motors produces the same shaft output power but uses less input power. So it produces same output as standard motor, but it uses lesser input power than a standard motor. Power factor is an expression of energy efficiency as in the ratio of true power in a circuit to the apparent power. True power is basically what power we are getting, and apparent power is basically what power is given, what is delivered to the circuit. So basically, poor power factor can result in heat damage to insulation and other circuit components, reduction in the amount of available useful power, require an increase in conductor and equipment sizes. So basically, demand, what is demand? That is also known as the apparent power. Here we can see that power factor is the ratio of true power to apparent power. So kVA, which is basically the apparent power, it is a measure of the amount of power used to run machinery and equipment during a certain period of time. So when if demand is greater than the power available, then this places a strain on the utility member. If suppose I require more power but only a certain amount of power can be applied. Then the supplier can impose restrictions by either by increasing the tax or increasing the cost of it, so that I try to mean, if obviously if the cost will increase, then we will try to stay in the limits without increasing the demand. Many utilities add a demand charge to the bills of large customers to offset difference between the supply and demand. Some energy conservation devices, such as CFL and pressurized steam stoves, mean basically in instead of using this box, etc., we can use steam cookers and solar cookers, which obviously uses less energy. The natural water cooler is a safe drinking water device which works on the principle of cooling by evaporation. No external source of energy, such as electricity or ice, is required. Normally, a tube light of 40-watt rating with a choke of 20 watts, so total it is 60 watt, is being utilized for street lights with a total power of 60 watt. Alternatively, the use of CFLs of 18-watt rating, which has an equivalent luminosity, would lead to a power saving to the extent of 70%, that is 42 watt. Also, the life of CFL are much longer than that of the tube light, with a cumulative saving on life as well as the energy consumption for the entire life. So here we can see basically the normal tube light and CFL. There is almost 70% conservation of energy if we use CFL in place of tube light. And moreover, its lifetime is quite large compared to tube light. So we are done with the theory part. Let us come to the assignment question. Shall I start? Hello. Hello. Just a second. Just a second. Give me. Should I start with the assignment questions? Just say yes or no, someone. Hello. Are you guys here? Okay. Which slide number do you know? Matlab, do you remember? Okay, I am showing you. Tell me which one. Okay. Okay. Anaerobic digestion. This one? Venugopal, say yes or no. This one or another slide? Am I not audible to you guys? Hello. What's happening? Venugopal, am I not audible? Mean, you can speak. At least say yes or no. If I'm not audible, then I will do something about it. Hello. Am I audible? Hello. Venugopal. Hello. Okay then. Next slide now I'm showing. This one, right? You can take a look. This one or the next one also I will show. Next one. Just give me a minute, you guys. Just a second. What did you do? Access the portal for the people. Okay, so just send me your, send your email ID in the chat box. I will send you this PPT or all the PPTs you need, Venugopal. Okay, okay, I will send you. Let me write your email ID. Just a second. Okay, then should I start with the question answer? Sorry, assignment question. Okay, let me start. We have, don't have enough time. Okay, then. Okay, then first question. Which of the following is a thermochemical route used for the conversion of lignocellulosic biomass and municipal solid waste? So thermochemical route is basically we have not discussed in detail as we studied them during coal. So basically the answer is combustion. Thermochemical route is basically combustion, which we studied during the energy route, energy production from coal. So basically the answer is combustion. As we know that briquetting is physical method, mechanical extraction is also physical method, and then fermentation is biological. So second question, which of the following product is normally formed by the anaerobic digestion of the lignocellulosic biomass and municipal solid waste? So during anaerobic digestion, we have studied the product formed is biogas. As we have seen that bio oil is used in transesterification. So this is the feedstock for transesterification. And biodiesel is formed from product of transesterification, that is chemical route. Product of transesterification. So this nitrogen is not produced in any of these methods, but biogas is. So this is the product of anaerobic digestion. Coming on to the third question, which is during methane production, the presence of lignin in feedstock biomass decreases the rate of. The answer to this is hydrolysis. So if lignin is present, then the rate of hydrolysis decreases and it becomes a rate determining step. As so here, as it is told that presence of lignin decreases the rate of hydrolysis. So it may so when the rate of hydrolysis decreases due to the presence of lignin, hydrolysis may be the rate limiting step. Coming on to the fourth question, which of the following are the conventional methods used for the production of bio-oils from oilseed? Conventional methods, as we have studied only four methods. So, as we know, this ultrasonicated assisted is the advanced method. Supercritical fluid extraction method is also advanced method. But these two are the conventional method. That is the expeller press method. That is directly extracting oil by pressing the oil seeds. And the solvent extraction method is basically the dissolving this oil, bio oil, in some kind of solvent for extraction. Question 5. Liquid formed by the densification of biomass roughly has a diameter greater than. Just now we studied it has a diameter greater than 30 mm. Moving on to the question 6. Which of the following is an organic binder? So organic binder we have seen that it includes bitumen. And this cement, lime, and clay, they are inorganic binders as we studied just now. Coming on to the seventh question, identify the type of briquetting technology shown in the following picture. As we know that we studied two type of one was the press. Just a second. One was this, that is piston press, and the second one is screw press or screw extruder. So here this is the screw press. Find the expression used to calculate interior lightning power allowance ILPA, where LPD is lightning power density and GLFA is the gross lighted floor area. So just now we studied this formula, which is ILP equals to sigma GLFA into LPD. So this one is the correct answer. Coming on to one of the numerical questions, a 10-ton hydraulic jack was used to lift the machine components and compress the briquettes. The reading of pressure gauge connected to hydraulic press, compaction press is 15 kilonewton per meter square. So this is the pressure given. Calculate the compaction force using the pressure value read from the pressure gauge. And the machine has 30 molds and the diameter of the briquette is 30 millimeters. So here what we have to calculate? We have to calculate the compaction force. Basically, we have to calculate the force. So the formula is pressure, as we all know, formula is pressure equals to force upon area. Simple formula we have to use here. So area of briquettes we have to calculate all the briquettes. So it will be 30 briquettes are there into area of 1. It is pi by 4 t square. So it will be pi by 4 into 0.03 meter square. So it will be giving us 0.021 meter square. So this is the area and force is given us in the question. So pressure will be, sorry, just a second. Pressure is given in the question. We have to calculate force. So it will be force equals to area into pressure. So area is 0.021 meter square into 15 kilonewton per meter square. So it will give us 318 Newton or 0.318 kilonewton. So my answer is 380 Newton. Is this clear? Now coming on to the next question, which is also a numerical question. Calculate the annual energy saving when 340 tube lights, each with 60 watt and 20-watt choke, originally deployed are replaced with 20-watt CFL lamps. Assume average working time is 12 hours per day. So here we can see that 340 tube lights are replaced with 20-watt CFL lamps. So total power of this tube lights will be 60 plus 20 watt, will be 80 watt, as we have seen 60 watt and 20-watt choke is also there. And then CFL is 20 watt. So for tube light, will cost us 12 into 365. As we have seen, annual energy saving we want. So 12 hours, 12 working hours are there per day. So 12 into 365 days per year are there. So it will give us 350.4 kilowatt hour. So this is the power used per year by the tube light. For CFL, it will be 20 into 12 into 365, which will give us 87.6 kilowatt hour. So the annual saving is 350.4 minus 87.6. It will give us annual saving, which is 262.8 kilowatt. So answer is 262.8 kilowatt hour. Is this clear? At least say yes or no, guys. Okay. Let's move forward. Coming on to the next question, which is which of the following municipal refuse components has the highest moisture content? So for that, let's come to this table. Highest moisture content, as we can see, consists of garbage. Garbage or greens and grasses has the highest moisture content. So the highest moisture content is basically garbage, as we can see in that table. Which of the following municipal refuse components has the highest heating value? So highest heating value is in that table. It is food crates, boxes, and scrapes. It is basically this one. It has the least amount of moisture content, so highest heating value. So, which of the following is not a process of biological conversion of biomass to energy? Sorry, which of the following is not a process of biological conversion of biomass to energy? So, fermentation is biological conversion. Anaerobic digestion is biological conversion. Microbial fuel cell is also biological conversion. So, transesterification, as here we can see, it is the chemical conversion. Coming on to the next question. Acidogenic bacteria include dash species. So, Clostridia and Acetobacteria is acetogenic bacteria, whereas here we can see that Lactobacillus is acidogenic bacteria. So the answer is Lactobacillus. Lactobacillus. These are acetogenic. This is acidogenic. Identify the correct statement regarding the kinetics of methane production. Presence of lignin decreases the rate of hydrolysis. So this is the correct answer, as we have just now in the other question we have studied, talked about this one. The question is, during methane production, the presence of lignin in feedstock decreases the rate of hydrolysis. So as it is asked which step is correct. So obviously this step, first step is the correct answer. Dash and dash precludes growth of methanogenic bacteria and thus reduces methane production. So as we have seen that methanogenic bacteria require low pH and high retention time. Sorry, just a second. So here we can see, sorry, it requires high pH and high retention time. So if opposite is done, low pH and low retention time is done, then as we can see here, here also it is told for that methanogenesis more days are required. So high pH and high retention time is required. So if we apply otherwise condition that low pH and low retention time, then methane production will be reduced. So that's why the answer is low pH and short retention time. Got it? Identify X and Y below. So here in this is the flow sheet for the biodiesel production from various feedstocks. So this one, as we have studied, it is vegetable oil X, and this one was recycled greases. Moving on to the next question, which of the following saturated fatty acids has the highest melting point? Answer is stearic acid, because linolenic and linoleic acid, these are unsaturated acids, as we have, I can show you. I have not shown it, sorry. So in this only stearic acid is the saturated fatty acid. These are unsaturated fatty acids, so the answer is stearic acid. In biodiesel refining, biodiesel once separated from the glycerine goes through a series of cleanup or purification steps to remove which of the following compounds. So basically, excess alcohol is also to be removed and excess residual catalyst needs to be removed. So answer is both A and B because it consists, as we have seen that after the biodiesel refining, methanol recovery takes place. And if there is extra free fatty acids, then we introduce excess catalyst also. So this catalyst also needs to be removed. So the answer is both A and B. Coming on to the last question for the course also and for the class also. So this is a numerical question. Okay, then let me start this. This is a bit lengthy question. So the bio oil extracted from an oil seed sample has 85% triglycerides containing three long chains, which can produce methyl esters of lauric acid, myristic acid, and palmitic acid in equal molar ratios during transesterification using methanol and NaOH catalyst. Calculate the amount of biodiesel produced by the transesterification of 10 kg of bio oil. Assume efficiency of the conversion is 78% and 14% palmitic acid is converted to soap. How much glycerol will be produced and how much soap will be produced? Okay then. So as we have seen, it is given that these three acids are formed. These three methyl esters are formed. Sorry, methyl esters. So let us first write down the equation. What will be formed and what is the feedstock. So this is lauric acid. It is CH3, CH210, COO, CH3. It can be written as C11H23. How we will determine the uh, formula for triglyceride? This is the method to determine the formula for triglyceride. So we will write it down like this. All this will be, we will write it collectively as C11H23. Also, we will write the molecular weight form. Then the second one is myristic acid, which is given as it can be written as this, and this palmitic acid, which is also used for the production of soap, will be written as this. So in the theory, as we studied, that the triglyceride formula will be this is the methane that we have added, and this is the other R part. So it will be the formula is basically it will be like this. C11H23, C13H27, H31. If we react this with CH3OH, then it will give us glycerol, and its molecular weight is 92 gram, and its molecular weight is 722 grams. Plus these three methyl esters. These three methyl esters will be formed. This is basically our reaction, and it is done in the presence of NaOH. So let us start with the question. So let us take basis as basis is given 10 kg of bio oil is used. The triglycerides present are, as we can see here, 85% triglycerides are present in the bio oil. So it will be 10 into zero point 0.8, so it will be 8.5 kg. So moles of triglycerides, if we see, it will be 8.5 0.722. As we have seen, it is 722 grams molecular weight. So it will, in kg, it will be 0.722. So we will get 11.77 moles. So now coming on to moles of triglycerides converted to glycerol. So according to the equations, efficiency of conversion is 78%. So this triglyceride is converted to 78% into this and glycerol. As we can see that 1 mole of triglyceride gives 1 mole of glycerol. So it will be moles of triglyceride will be 11.77 into 0.78. So the moles of glycerol will be 9.8182 moles. Now glycerine produced or glycerol produced is basically 9.182 into, it is 92 grams, so it will be 0.92 kg, which will give us 0.844 kg of glycerol produced. Now coming on to mass of lauric acid produced. So from the equation, we can see that if 1 mole of glycerol is produced, then 1 mole of lauric acid, 1 mole of palmitic acid, and 1 mole of myristic acid. So the moles will be same. It is 9.182 into 0.214. 5.214 because the molecular weight is 214, that is in kg 0.214. So it will give 1.96 kg of lauric acid. Mass of myristic acid produced 9.182 into 0.242, which is the molecular weight. It will give 22.22 kg. Now mass of palmitic acid produced 9.182 into 0.270. But here we can see in the question that 14% of palmitic acid is converted to soap. So 14% is converted to soap. So remaining 86% is only formed here. So it will be 86%. 2.132 kg of palmitic acid is converted. In this glycerides, this triglyceride produces palmitic acid, out of which 14% is converted to soap. So only here 86% is left. 86% of palmitic acid is left in this palmitic acid form, and the rest 14% is converted to soap. Just a second. Now moving forward, palmitic acid used for soap formation. So here we have seen that out of this only 0.86 is palmitic acid. So remaining 14% will be soap. So it is 9.182 into 0.270 into 0.14. It will give us 0.347 kg of soap is produced. Okay. So now coming on to mass of biodiesel wheat what. So in the question reaction, we can see that biodiesel components include these three parts. So adding the mass of these three, we will be getting biomass. So adding this, and this, we will get our biomass. So it is 1.964 kg of lauric acid, 2.22 kg of myristic acid, and 2.132 of palmitic acid, which will give us 6.316 kg of bio oil produced. Sorry, biodiesel produced from 10 kg of bio oil. So now, coming on to how much soap is produced. Reaction of soap formation. Let us come to the reaction of soap formation. So palmitic acid is used, which is C15H31COOCH3. It will react with NaOH to form soap. So it will be C15H31COONA, which is soap basically. And its molecular weight is 278 grams. And molecular weight of this we have known it is 270 grams. Plus it will give methanol. So we can see here that 270 gram of P15H31COOCH3 will produce 278 gram of soap. So how much is used for the conversion? Palmitic acid used for soap preparation is this. So 0.347 kg of this palmitic acid produces 278 by 270 into 0.347. So it will give us 0.357 kg of. So the answer is, we have seen answer is, we have to calculate what we have to calculate. We have to calculate the amount of glycerol produced and soap produced. So glycerol produced is this 844 kg and soap is this 357 kg. So the answer is 844 kg and 357 kg. Sorry, 0.844 kg and 0.357 kg. Is this clear? This question is clear to you guys? Venugopal? Okay. Any other questions? Do you want to see any other slide or something? Otherwise, you will get these slides and questions you can, I mean, this video and slides you can easily get from the portal. So, so we end our tutorial session and we end our course also for this session. I hope I was clear during the session and I will just now add the PPT. I mean, after ending the class or maybe latest by 10 p.m. Okay, I will send you the PPT just now. I will mail you personally. Uh, just after ending the class, I will send you the PPT. That will be fine. When do you have exam, Venugopal? Okay, okay. I will send it just now. No issues. Any other issues? Should we end the class? Okay then. Thank you everyone. It was fun teaching you guys. Thank you so much. Okay then. Let's end the class for the day.